Hello there and welcome to Life Beyond Seen, a quiet place where big questions are allowed to move slowly, where science doesn't rush you, and where curiosity is treated like something warm you can hold rather than a puzzle you have to solve. This is a space made for easing out of the day, for letting thoughts stretch without snapping, and for following ideas wherever they happen to wander, even if they wander far back in time. Tonight, we're going to drift into a world that once felt heavier, denser, and in many ways larger than the one beneath your feet right now. Long before traffic lights, smartphones, and bedtime routines, Earth carried animals that would feel impossible if you met them today. Oceans where a single bite could swallow a modern shark whole. Forests where a snake longer than a city bus slid through humid shadows. Plains where footsteps shook the ground as creatures taller than houses moved slowly but decisively through their territory. These weren't legends or exaggerations. They were ordinary animals for their time, born into a planet that seemed comfortable with excess. Tonight's journey is about those giants, and more importantly about a quieter question hiding behind them. Why did Earth once build creatures so enormous, and why did it stop? If you pause for a moment and picture the largest land animal alive today, an elephant, it already feels impressive. Its weight presses into the soil. Its bones carry a history written in mass and patience. And yet, compared to some of the beings that came before, it is modest. A survivor rather than a ruler. The giants of the past were not just slightly larger versions of what we see now. They lived in a different balance altogether. One where size was not an exception, but a strategy that worked. The planet allowed it, supported it, encouraged it even. As you settle in, perhaps lying down or letting your eyes rest somewhere comfortable, consider where you are listening from right now. Maybe it's late evening and the room is quiet except for distant sounds. Maybe it's early morning, the day just beginning to stretch awake. Somewhere on Earth, the ground beneath you is thin compared to what once lay above oceans and forests ruled by giants. That same planet still turns, still breathes, but it no longer grows bodies on that scale. Not on land, not anymore. If this kind of slow exploration feels soothing, or if you enjoy letting your mind wander without needing to arrive anywhere in particular, a simple like or subscription helps keep this space going. It lets this calm corner reach others who might need a quiet place to rest their thoughts too. Nothing urgent, nothing demanded, just a small gesture that keeps the lights low and the doors open. Now, let's begin easing into the story itself, because the disappearance of giants wasn't sudden, and it wasn't dramatic in the way movies like to show it. There was no single moment when Earth decided to stop building enormous animals. No announcement, no sharp dividing line. Instead, it was a slow shift, the kind that only becomes obvious when you look backward over millions of years. The planet changed, not out of cruelty or intent, but because planets do what they do. They cool, they warm, they rearrange oceans and continents, and life, always opportunistic, adjusts until it can't. To understand why Earth no longer builds giants, it helps to first imagine a world where being huge was not a disadvantage. A world where warmth wrapped the planet like a blanket, where food was not scarce, but spread generously across land and sea, where oxygen levels made breathing easier and growth less costly. In such a place, large bodies were not burdens, they were tools. They meant fewer predators, longer lifespans, and more stable dominance over territory. Size was safety. Size was efficiency. Size was success. The ocean especially rewarded enormity. Water carries weight differently than air. It allows bodies to grow heavier without collapsing under themselves. That's why even today the largest animals on Earth live beneath the waves. But millions of years ago the seas offered even more than buoyancy. They offered warmth, rich food chains, and vast spaces where energy could be converted into mass without tight limits. In those conditions, creatures like enormous prehistoric sharks didn't need to rush. They didn't need speed alone. They could afford patience, power, and overwhelming presence. On land, the story was more delicate but no less impressive. Warm climates meant plants grew fast and tall. Forests recycled nutrients quickly. Herbivores could grow large because food was reliable, and predators grew large because their prey did. This feedback loop pushed bodies upward in size generation after generation. Bones thickened, muscles expanded, hearts adapted, metabolisms adjusted. Life explored how big was still workable. But size is never free. Every increase in mass comes with a cost. Bigger animals need more food, they need more stable environments, they need time to grow and reproduce, they move slower, they adapt more slowly. In a stable world, those costs are manageable. In a changing world, they become dangerous. Earth, as it turns out, is not sentimental. As climates cooled and warmed unevenly, as continents drifted and oceans reshaped currents, the systems that once supported giants began to wobble. Not collapse all at once, but fray at the edges. Seasons became harsher. Food chains shortened. Oxygen levels shifted. The margin for error shrank. Smaller animals, quicker to adapt and easier to feed, began to thrive where giants struggled. Extinction, in this sense, wasn't a dramatic ending. It was a gradual mismatch between bodies built for abundance and a world offering less of it. Giants didn't disappear because they were failures. They disappeared because they were specialists in a version of Earth that no longer existed. This is why modern animals tend toward moderation. Not because evolution lost its imagination, but because today's planet rewards efficiency over excess. Being smaller means needing less, reproducing faster, adapting quicker, surviving uncertainty better. The rules changed, and life followed them. And yet traces of that ancient giant-friendly world still linger. In the deep ocean, in the slow heartbeat of large mammals, in the way certain ecosystems still stretch toward size when given the chance. These are echoes, reminders that Earth is capable of building giants again under the right conditions. As we move forward from here, we'll start meeting those ancient animals not as monsters or myths, but as products of their time. Creatures shaped carefully by the physics, chemistry and climate of the planet they lived on. Understanding them means understanding Earth itself, not as a static place, but as a living system that quietly decides what kinds of bodies it will allow to exist. And as that picture sharpens, the question of why Earth no longer builds giants becomes less mysterious, and more like a conversation between life and the planet it inhabits, one that never truly ends, only shifts its tone, long before familiar coastlines settled into their current shapes, before ice caps claimed the poles and deserts spread where forests once stood. Earth was a planet that made room for size. Not symbolically, not poetically, but physically and chemically. The ground, the air, the oceans, and the climate all leaned quietly in favour of bodies that grew large, heavy, and slow. This was not a world that merely tolerated enormity. It supported it, sustained it, and in many cases rewarded it. To understand this, it helps to stop thinking of Earth as a static stage, where animals simply appear and disappear, and instead see it as an active participant. The planet itself sets conditions. It decides how much energy flows through ecosystems, how predictable seasons are, how stable temperatures remain, and how easy it is for living tissue to grow, repair, and persist. In the deep past, many of those conditions aligned in ways that made large size not only possible, but practical. One of the most important differences between ancient Earth and the world we know now was temperature. For long stretches of geological time, Earth was warmer overall. Not just slightly warmer, but consistently so across vast regions. There were no permanent ice caps at the poles. Tropical and subtropical climates reached far into what are now temperate zones. Winters, where they existed at all, were milder and shorter. This matters because warmth reduces the energy cost of survival. An animal does not need to burn as much fuel just to stay alive when its surroundings are already warm. Less energy spent on basic maintenance means more energy available for growth. Warmth also changes how ecosystems behave. Plants grow faster when temperatures are stable and warm. They photosynthesize more efficiently, especially when paired with higher levels of carbon dioxide, which were common during many periods of Earth's past. Faster plant growth means more food at the base of the food chain. That abundance travels upward. Large herbivores can afford to exist when vegetation is not only plentiful but reliably so. Large predators can afford to exist when their prey is abundant and predictable. Then there is oxygen. While the exact levels varied over time, there were periods when atmospheric oxygen was higher than it is today. Oxygen is not just something animals breathe, it is a limiting factor in how big bodies can grow. Muscles require oxygen to function. Large bodies require efficient oxygen delivery systems. When oxygen is plentiful, those systems can support greater mass without failing. This is one reason why ancient insects, for example, reached sizes that would be unsustainable now. While the giants we are focusing on were not insects, the same principle applies. Higher oxygen availability lowers the physiological cost of size. The oceans too played a critical role. Water supports weight in ways air cannot. Buoyancy allows bodies to grow heavier without collapsing under their own mass. But ancient oceans were not just supportive. They were warm, shallow in many regions, and rich in nutrients. Continental shelves were broader. Sea levels were higher. Sunlight penetrated wide expanses of water, fueling plankton growth. Plankton fed small fish. Small fish fed larger ones. Energy flowed upward through the food web with relatively few bottlenecks. In such conditions, being large was efficient. A massive marine predator could travel long distances with relatively low energy expenditure. It could store energy in its body and survive periods when food was less available. It could dominate territory without constant conflict. Size reduced vulnerability. Few predators could threaten a fully grown giant. Survival became less about speed and more about endurance. On land, the picture was more complex but still favourable. The landscapes of the past were shaped by slow, long-term stability. Continents moved, but slowly. Mountain ranges rose and eroded over millions of years. Rivers carved paths that remained for ages. This stability allowed ecosystems to mature deeply. Forests grew dense and tall. Plant diversity increased. Herbivores evolved to process massive amounts of plant material. Their digestive systems became efficient factories for turning cellulose into usable energy. Large herbivores changed the land itself. Their movement trampled vegetation, spread seeds, and altered soil composition. In doing so, they created feedback loops that supported further plant growth. Predators evolved in response, growing larger to hunt larger prey. This was not a race toward maximum size, but a gradual escalation shaped by opportunity rather than pressure. Another factor that favoured giants was predictability. Ancient ecosystems, while not static, often experienced long periods without abrupt disruption. There were catastrophes, of course, but between them were millions of years of relative consistency. For a large animal, predictability is essential. Long gestation periods, slow growth rates, and extended lifespans all require an environment that does not change too quickly. When conditions remain stable, those traits become advantages. A large animal that lives a long time can reproduce multiple times, spread its genes widely, and maintain dominance over generations. It is easy to forget how young many modern environmental pressures are. Rapid climate shifts, extreme seasonal variability, and frequent ecological disturbances are more common now than they were during many giant-friendly eras. The Earth of the past moved at a slower tempo. Change happened, but it unfolded over spans long enough for large-bodied species to adapt. Even gravity plays a subtle role. Earth's gravity has remained relatively constant, but its interaction with other factors matters. When organisms evolve under conditions where food is abundant, temperatures are warm, and oxygen is plentiful, gravity becomes less of a constraint. Bones can thicken, muscles can strengthen, circulatory systems can expand. Over time, bodies learn how to manage their own weight. It is also important to understand that these giants were not clumsy mistakes of evolution. They were well-adapted, finely tuned organisms. Their bones show internal structures designed to support mass efficiently. Their muscles were arranged to minimize energy loss. Their behaviors reduced unnecessary movement. Many giants were not fast because they did not need to be. Their presence alone reshaped their environment. The planet itself, through its chemistry and physics, made all of this viable. Soil nutrient cycles were robust. Volcanic activity replenished minerals. Weathering processes returned nutrients to ecosystems. The carbon cycle moved differently, storing and releasing energy on timescales that favoured long-term growth rather than rapid turnover. In this context, the existence of enormous animals feels less surprising. It feels almost inevitable. Given enough time, enough energy, and enough stability, life will explore size. It will push upward until it finds the limits. And for a long while, those limits were far higher than they are now. But even in this giant-friendly world, there were boundaries. Size always carried risks. Large bodies are harder to cool. They require complex systems to manage heat. They are slower to reproduce. Their young are vulnerable for longer periods. These risks were manageable only as long as the environment remained supportive. Subtle changes began to erode that support. Temperature gradients increased. Seasonal extremes became more pronounced. Ocean currents shifted as continents rearranged themselves. Sea levels fluctuated. Food webs became less predictable. Each change on its own was survivable. Together they began to tilt the balance. Smaller animals gained advantages in this shifting landscape. They required less food. They matured faster. They adapted more quickly. They could exploit niches that giants could not. Over time, ecosystems reorganized around these traits. The planet did not reject giants outright, but it stopped favoring them. What makes this transition so fascinating is how gradual it was. There was no single moment when Earth crossed a line and giants vanished. Instead, there were overlapping eras where large and small coexisted, where size was still possible but increasingly costly. Some giants persisted longer than others, especially in environments that retained stability, such as deep oceans. This is why the story of Earth's giants is not one of failure. It is a story of changing priorities. The planet shifted the conditions under which life operates, and life responded accordingly. Evolution did not abandon size. It simply followed the rules that made survival most likely. As we continue forward, it becomes important to meet the giants themselves as products of this world, shaped by it rather than standing apart from it. They were not anomalies. They were expressions of what Earth could be, given the right balance of energy, stability, and time. And as that balance shifted, the giants became less common, not because the planet lost the ability to create them, but because it no longer offered the long-term support they required. That quiet transition from a world that favoured enormity to one that rewards efficiency sets the stage for understanding the creatures themselves and why their absence today tells us so much about the Earth we live on now. The planet continues to change, slowly and relentlessly, and life continues to respond. Size has not vanished as an idea. It has simply been reshaped, constrained, redirected. The echoes of that older, larger world still linger, waiting to be understood as part of an ongoing conversation between Earth and the life it carries. To really understand why Earth once favoured enormous life, it helps to slow down and meet the giants themselves, not as exaggerated monsters or cinematic villains, but as real animals that woke up, hunted, rested, and survived day after day in environments that made sense to them. Megalodon, Titanoboa, and Tyrannosaurus rex did not exist as symbols of terror. They were not mistakes or freaks of nature. They were solutions. Each one represented a precise answer to the conditions of its time, shaped carefully by millions of years of natural selection. Let's begin in the ocean, because the sea has always been the most forgiving place for size. Megalodon lived in a world where the water itself helped carry its mass, where temperature and food availability created an open invitation for something very large to thrive. This was not the modern ocean, fragmented by colder currents and depleted ecosystems. It was warmer, richer, and far more uniform in many regions. Large prey animals were common, including early whales and massive fish that moved slowly enough to be worth the energy of pursuit. Megalodon was not built for constant speed. Its body was designed for power and efficiency. A massive tail provided steady propulsion rather than quick bursts. Its jaws, wide and reinforced, could deliver catastrophic force without prolonged struggle. Teeth the size of a human hand were not there for decoration. They were tools evolved specifically to process thick bone and dense muscle. This was an animal that could afford to wait, to choose targets carefully, and to conserve energy between meals. Importantly, Megalodon did not need to eat constantly. Its size allowed it to store energy efficiently, and its environment provided enough large prey to make infrequent but substantial meals possible. This balance is critical. A giant predator cannot survive in a world where food is unpredictable or scarce. Megalodon's oceans offered reliability. Migration routes were stable. Water temperatures did not fluctuate sharply. Entire food chains supported large-bodied life at multiple levels. Megalodon was also widespread. Fossil evidence shows that it inhabited oceans around the globe. This geographic flexibility further reduced risk. If conditions changed in one region, populations elsewhere could persist. The ocean, in this era, functioned as a connected system rather than a patchwork of isolated habitats. That connectivity mattered. Now shift your attention to land, but not to dry plains or cool forests. Picture instead a humid, tropical environment near the equator, thick with vegetation and heavy air. This is where Titanoboa lived. It existed not long after the extinction of the dinosaurs, during a period when Earth's climate was exceptionally warm. Average temperatures in some regions were several degrees higher than today. Rainfall was abundant. Forests were dense and sprawling. Titanoboa was not fast. It did not need to be. Like modern large snakes, it relied on stealth, patience, and ambush. But unlike anything alive today, it reached lengths that strain modern imagination. This was possible for a simple reason. Snakes are ectothermic. They rely on environmental heat to regulate their body temperature. In cooler climates, size becomes a liability because larger bodies are harder to warm. In Titanoboa's world, warmth was constant. Heat was not something to seek. It was everywhere. This allowed Titanoboa to grow without the metabolic penalties that limit large reptiles today. Its muscles functioned efficiently. Its digestion proceeded steadily. Its movement, though slow, was powerful enough to subdue large prey, including massive fish and crocodile-like animals. In water, where buoyancy assisted its mass, Titanoboa was even more formidable. Rivers and swamps provided ideal hunting grounds, combining cover, warmth, and large prey. Titanoboa's existence tells us something important. Giant size does not require advanced intelligence or complex behavior. It requires conditions that reduce energetic costs and stabilize survival. Titanoboa did not dominate through speed or strategy. It dominated because its environment allowed its body plan to scale up without breaking. Now move forward again in time, to a land ruled not by reptiles that basked and waited, but by animals built for active dominance. Tyrannosaurus rex lived in a world that was still warm, still productive, but beginning to show more variability. Forests alternated with open plains. Seasons existed, though they were milder than today. Large herbivorous dinosaurs were abundant, creating opportunities for large predators. Tyrannosaurus rex was not simply large. It was engineered for its role. Its legs were powerful, capable of supporting its mass while allowing sustained movement. its skeleton balanced strength and efficiency, with hollow bones that reduced weight without sacrificing durability. Its skull was a complex structure designed to withstand enormous forces. Bite marks on fossilized bones show that it could crush bone deliberately, not accidentally. Unlike Megalodon or Titanoboa, Tyrannosaurus rex likely required more frequent feeding. As a warm-blooded animal, it had higher metabolic demands, but its environment could support this. Large prey animals were common. Competition existed, but Tyrannosaurus rex sat near the top of the food web. Its size reduced threats from other predators. Its senses, especially smell, were highly developed, allowing it to locate food over long distances. There is ongoing debate about how much Tyrannosaurus rex hunted versus scavenged, but this debate itself highlights an important point. A giant predator does not need to rely on a single strategy. Size allows flexibility. Whether pursuing live prey or claiming carcasses, Tyrannosaurus rex could afford to be selective. Its presence alone could displace smaller predators. What unites these three giants is not just their size, but the way their bodies fit into their worlds. None of them existed in isolation. Each was part of an ecosystem that supported large size at multiple levels. Large prey, stable climates, predictable resources, and long evolutionary timeframes all contributed. Another shared trait is longevity. These giants did not live fast, short lives. They grew slowly. They matured over years or decades. This slow life history only works in environments where survival rates are high enough to justify delayed reproduction. High juvenile mortality would doom such species quickly. Their worlds were stable enough to allow young to survive and adults to persist long enough to reproduce multiple times. It is also worth noting that giants often shape their ecosystems rather than simply inhabit them. Megalodon influenced whale evolution. Prey species adapted in response to its presence, altering size, speed, and migration patterns. Titanoboa affected river ecosystems, controlling populations of large aquatic animals. Tyrannosaurus rex influenced the behavior and distribution of herbivorous dinosaurs, shaping landscapes indirectly through fear and movement patterns. These giants were not rare accidents. They were keystone species. Remove them, and entire ecosystems reorganized. This is why their disappearance had ripple effect far beyond their own extinction. But their dominance was always conditional. It depended on the continuation of the conditions that built them. As Earth began to change, those conditions weakened. Ocean temperatures cooled, sea levels dropped, food chains shortened. On land, climates became more seasonal, extremes increased, forests fragmented, open plains expanded. Each change made large size slightly more expensive, slightly riskier. Smaller animals with faster reproduction and greater adaptability began to thrive. They filled niches that giants could not exploit efficiently. Over time, the balance shifted. Giants became fewer. Eventually, they vanished from land almost entirely. Meeting Megalodon, Titanoboa, and Tyrannosaurus rex in this way allows us to see them not as symbols of a lost world, but as mirrors reflecting what Earth once offered. Their size was not an anomaly, it was a response. As we continue, it becomes necessary to look beyond individual animals and examine the underlying rules that govern size itself. Why size becomes advantageous under certain conditions and why it becomes a liability under others. Because the disappearance of giants was not about bad luck or sudden catastrophe alone. It was about a gradual rewriting of the rules, one that continues to shape life on Earth right now, even if the giants themselves are gone. When we talk about size in nature, it's tempting to think of it as a simple contest. Bigger versus smaller, strong versus weak, winner versus loser. But size is not a trophy evolution hands out at the end of a race. It is a strategy, and like any strategy, it only works under certain conditions. There is no universal advantage to being large, just as there is no universal advantage to being small. Instead, nature follows a set of quiet rules that determine when size pays off and when it becomes a liability. The first rule is energy. Every living body is an energy system. It takes energy to grow, to move, to maintain tissues, to heal injuries, and to reproduce. Larger bodies require more energy overall, but not always more energy per unit of mass. In fact, one of the reasons large animals can exist at all is that metabolism scales in a non-linear way. A large animal does not need 10 times the energy of a smaller animal that is 1/10 its size. Its energy needs increase more slowly than its mass does. This means that gram for gram, larger animals are often more energy efficient. This efficiency creates advantages. A large animal can travel farther on the same relative energy budget. It can store more fat and survive longer periods without food. It can buffer itself against short-term shortages that would kill a smaller animal quickly. In stable environments with predictable resources, this efficiency favours size. When food arrives regularly and in abundance, large bodies are not wasteful, they are economical. But energy efficiency only works when energy is available. This leads to the second rule. Large size requires reliable input. A giant animal cannot afford uncertainty. Missing one meal may not matter to a mouse, but for a massive predator or herbivore, repeated shortages can be fatal. Large bodies take longer to recover. They cannot rapidly reproduce to compensate for losses. Their entire life strategy assumes that tomorrow will look roughly like today. This is why large animals tend to evolve in environments that are stable over long periods. Warm climates with mild seasonal changes, oceans with steady currents, landscapes where food sources do not disappear abruptly. When that stability breaks down, the advantage of size erodes quickly. The third rule is time. Size takes time to build. Large animals grow slowly. Their bones thicken gradually. Their muscles develop over years. Their nervous systems mature at a measured pace. Reproduction often comes later in life, and offspring require extended care or protection. This slow timeline only works when survival rates are high enough to justify it. If juveniles die frequently, large species collapse. If adults are removed faster than they can be replaced, populations cannot recover. This is why large animals are often the first to disappear during periods of rapid change. They simply cannot respond fast enough. The fourth rule involves heat. Managing body temperature becomes increasingly difficult as size increases. Large bodies retain heat more effectively, which is an advantage in cooler climates, but a challenge in warm ones. Conversely, small bodies lose heat quickly, which can be fatal in cold environments, but helpful when temperatures rise. This is why many giant animals evolved in warm environments where overheating could be managed through behavior rather than physiology. Water immersion, shade, slow movement, and large surface areas for heat exchange all help. But when climates shift toward greater extremes, heat management becomes harder. Large bodies struggle to cool down during heat spikes and to warm up during cold snaps. The fifth rule concerns movement. Larger animals tend to move more slowly, not because they are incapable of speed, but because speed becomes expensive. Acceleration requires force, and force scales with mass. While some large animals can move quickly in short bursts, sustained high speed is rare. Instead, giants rely on presence rather than pursuit. They intimidate. They dominate territory. They wait. This strategy works when prey is abundant or slow, or when competition is minimal. It fails when food becomes scarce or evasive. Smaller animals can change direction quickly. They can hide in small spaces. They can escape in ways large animals cannot. Another quiet rule involves risk. Large animals experience fewer predators, but when something does go wrong, the consequences are severe. Injuries heal slowly, falls are more dangerous. Disease spreads through large populations with devastating effect, because reproduction cannot replace losses quickly. Size reduces some risks while amplifying others. This leads to an important balance. Large animals tend to evolve in systems where risks are low but consequences are manageable. As soon as unpredictable threats increase, whether from environmental shifts, new competitors, or sudden catastrophes, the balance tips against them. There is also a rule related to ecology itself. Large animals shape ecosystems, but they also depend on them being intact. Remove key plant species, alter nutrient cycles, or fragment habitats, and large animals suffer disproportionately. Smaller species can often persist in degraded environments. Large ones cannot. This is why modern ecosystems rarely support land giants. Human activity aside, the natural world today is fragmented. Habitats are smaller, food chains are shorter, seasonal extremes are stronger. Even without direct interference, the planet's current configuration does not favour enormous land animals. Importantly, the rule of size is not about intelligence or superiority. It is not a ladder where evolution climbs toward bigger forms. It is a set of trade-offs. Every increase in size solves some problems and creates others. Nature does not choose size because it is impressive. It allows size only when the math works. This is why the history of life shows repeated experiments with gigantism followed by retreat. Time and again, when conditions align, size increases. When conditions shift, size declines. There is no moral to this pattern, only responsiveness. Even today we can see these rules in action. In the ocean, where buoyancy and stable temperatures still exist, enormous animals survive. Whales remain the largest animals to ever live, not because evolution peaked with them, but because the ocean still supports their strategy. On land, where gravity, heat, and fragmentation impose harsher limits, size is constrained. The rule of size also explains why certain lineages repeatedly produce large forms while others do not. Body plans matter. Some designs scale better than others. Thick limbs, column-like legs, efficient circulatory systems, and strong skeletal frameworks all make large size more feasible. Animals that lack these features rarely grow beyond certain limits, no matter how favourable conditions become. But even the best designs fail when the environment withdraws support. No amount of structural efficiency can overcome chronic food shortages or rapid climate swings. At that point, the rules shift again, favouring speed, flexibility, and fast reproduction. Understanding the rule of size helps strip away the mystery from the disappearance of giants. They did not vanish because evolution lost ambition. They vanished because the balance of costs and benefits changed. Size stopped paying for itself. As we move forward, this rule becomes central, because once size is understood as a strategy rather than a goal, it becomes easier to see why Earth no longer builds giants in the way it once did. The planet did not forget how. It simply stopped offering the conditions under which size makes sense. And that shift, subtle and slow, continues to shape the animals we see around us today, from the smallest insects to the largest remaining mammals, all operating under the same quiet rules, even if the giants themselves are now only echoes of a different balance. When we strip away names and timelines and focus instead on the physical foundations of life, two forces rise quietly to the surface as some of the most important drivers of size Earth has ever offered: oxygen and warmth. Not as dramatic elements, not as abstract ideas, but as simple, measurable conditions that decide how much living tissue the planet can realistically support. When these two factors align in the right way, growth becomes easier. When they drift apart, growth becomes expensive, risky, and eventually unsustainable. Oxygen is often talked about as if it were merely fuel for breathing, but in living systems it is far more than that. Oxygen is a gatekeeper. It controls how efficiently cells can convert food into usable energy. Every muscle contraction, every nerve signal, every process of repair and growth depends on oxygen being delivered at the right rate. As bodies grow larger, delivering oxygen becomes more difficult. Distances inside the body increase, tissues become thicker, the circulatory system must work harder to move oxygen from the outside world to the deepest cells. In today's atmosphere, oxygen makes up about 21% of the air. That figure feels stable and permanent to us, but across Earth's history it has fluctuated dramatically. There were long stretches when oxygen levels were significantly higher. Even small percentage increases have enormous biological consequences. Higher oxygen availability means that each breath delivers more usable energy. Muscles fatigue less quickly. Growth requires fewer compromises. Large bodies can function with greater safety margins. This does not mean that oxygen alone creates giants, but it removes one of the most important constraints that usually keeps size in check. With more oxygen available, the cost of building and maintaining large muscles drops. Recovery from exertion improves. Circulatory systems can afford to be less extreme. The body does not need to push every system to its limits just to stay alive. Warmth works alongside oxygen in a complementary way. Temperature governs the speed of chemical reactions inside cells. Warmer environments allow biological processes to proceed more efficiently. Enzymes function within optimal ranges. Digestion is faster. Growth occurs with fewer interruptions. For animals that rely on external heat like reptiles, warmth is essential. Without it, large size becomes impossible. A massive, cold-blooded body in a cool environment would struggle to move, digest, or even survive. During many periods when giants flourished, Earth's average temperatures were higher and more evenly distributed. The difference between equator and poles was smaller. Seasonal swings were gentler. There were fewer prolonged cold spells that forced animals to burn energy just to maintain basic function. Warmth was not something to chase. It was ambient. This matters deeply for growth. When warmth is stable, bodies can afford to be large without developing complex internal heating systems. This is one reason reptiles once reached sizes that would be impossible for them today. Their physiology did not change dramatically. The environment did. A warm world allows ectothermic animals to behave almost as if they were warm-blooded without paying the metabolic price. Even for endothermic animals, those that generate their own heat, warmth reduces energy demands. Less energy spent on thermoregulation means more energy available for growth, reproduction, and repair. Large mammals and dinosaurs alike benefited from environments that did not constantly drain their reserves. Oxygen and warmth together create a multiplier effect. Higher oxygen increases energy efficiency. Warmth accelerates biological processes. Combined, they allow life to build mass more easily and maintain it with fewer trade-offs. Growth becomes something the environment encourages rather than resists. But these conditions did not exist in isolation. They were part of a larger system. Warmer temperatures often coincided with higher carbon dioxide levels, which enhanced plant growth. Lush vegetation fed herbivores. Herbivores fed predators. The entire food web expanded upward. When the base of the pyramid grows broader and more productive, the top can rise higher without collapsing. In such worlds, growth was not rushed. Animals could take years to mature without facing constant survival pressure. Juveniles could grow slowly and steadily. Adults could invest energy in maintaining large bodies rather than constantly repairing damage from environmental stress. Longevity became possible, and longevity favors size because it allows delayed reproduction to pay off. The Earth itself facilitated this growth through geological processes. Volcanic activity released gases that enriched the atmosphere. Weathering of rocks added nutrients to soil and oceans. Continental arrangements created vast shallow seas that absorbed sunlight and supported plankton blooms. These were not deliberate acts. They were outcomes of planetary physics, but life responded by expanding into the available space. As oxygen levels gradually declined and temperatures began to fluctuate more dramatically, the balance shifted. Even modest drops in oxygen increased the cost of large size. Circulatory systems must work harder. Tissues become more vulnerable to stress. Growth slows. Recovery takes longer. At the same time, cooling climates introduce new challenges. Maintaining body temperature becomes expensive. Seasonal scarcity becomes common. Warmth is no longer guaranteed. These changes do not need to be extreme to matter. Large bodies operate close to their limits even in favourable conditions. Remove a small percentage of support and the margin disappears. What was once efficient becomes precarious. What was once safe becomes risky. It is important to understand that this shift did not immediately erase giants. For long periods, large animals persisted even as conditions worsened. They adapted behaviourally, they migrated, they changed diets, but adaptation has limits, especially for bodies built on the assumption of abundance and stability. As oxygen availability continued to fluctuate and climates became more variable, smaller bodies gained an edge. They required less oxygen overall. They heated and cooled more quickly. They could exploit microhabitats that buffered temperature extremes. They reproduced faster, allowing populations to rebound after disruptions. This does not mean that modern Earth is oxygen poor or cold in an absolute sense. It means that the combination of oxygen levels, temperature stability, and ecological productivity no longer aligns in a way that favours extreme size on land. The planet still supports growth, but it rewards moderation. In the oceans, where temperatures are buffered and oxygen delivery is aided by water movement, size remains viable. That is why the largest animals that have ever lived still exist today beneath the surface. The conditions that once supported giants on land now persist mostly in water. On land, gravity amplifies the cost of size. Bones must support weight continuously. Joints wear down. Heat builds up during movement. Without the environmental generosity of the past, these costs become prohibitive. Evolution responds not by abandoning size entirely, but by limiting it. Oxygen and warmth are not just background conditions. They are active constraints that shape what kinds of bodies can exist. When they are plentiful and stable, life explores scale. When they become limited or unpredictable, life retreats toward efficiency. This understanding reframes the disappearance of giants as a planetary shift rather than a biological failure. Earth did not decide to stop building giants. It simply changed the conditions under which growth was cheap. And when growth becomes expensive, evolution looks for other solutions. As we continue forward, this foundation becomes crucial. Because once we understand how oxygen and warmth set the stage for growth, we can begin to see how other factors, like food availability and ecosystem structure, either amplify or undermine that stage. The giants were not built in isolation. They were built on a planet that, for a time, made growing large the easiest thing to do. There is a simple truth that sits beneath every story of giants, one that is easy to overlook because it sounds almost too ordinary to matter. Large bodies cannot exist without large amounts of food. Not occasionally, not in bursts, but consistently, predictably, and across long stretches of time. The age of giants was, above all else, an age when food was not just available, but abundant in a way that reshaped the entire structure of life on Earth. When we imagine the distant past, it is tempting to picture harsh, untamed worlds where survival was constant struggle. In reality, many of the periods that produced giants were remarkably generous. Productivity was high. Energy flowed smoothly from sunlight into plants, from plants into herbivores, and from herbivores into predators. The bottlenecks that limit modern ecosystems were either weaker or absent altogether. At the base of this abundance was plant life. Ancient Earth supported vast expanses of vegetation, fueled by warm temperatures, high carbon dioxide levels, and long growing seasons. plants could photosynthesize efficiently for much of the year. Forests spread across continents that are now deserts or temperate grasslands. Wetlands and floodplains were common, constantly replenished by rivers that carried nutrients from eroding mountains. These landscapes did not just look green, they were energetically rich. Leaves were thick, stems were fibrous, growth was rapid. When plants died, decomposition returned nutrients quickly to the soil, creating a cycle that reinforced itself. This constant renewal meant that herbivores could feed without exhausting their environment, at least not in the short term. Large herbivores thrived in this setting. Size allowed them to process enormous quantities of low-quality plant material efficiently. A large digestive system could extract energy from tough vegetation that smaller animals could not survive on. What might be wasteful or indigestible to a small body became usable fuel in a large one. As herbivores grew larger and more numerous, they created opportunities for predators. Importantly, this did not require predators to hunt constantly. Large prey meant large meals. A single successful kill could sustain a giant predator for days or even weeks. This reduces the energetic cost of survival. Instead of constant motion and frequent risk, predators could afford patience. In the oceans, this dynamic was even more pronounced. Phytoplankton formed the foundation of marine food webs. In warm, nutrient-rich waters, plankton blooms were massive and frequent. These blooms fed vast populations of small organisms, which fed larger fish, which in turn supported enormous predators. Energy transfer was efficient enough to support multiple levels of large-bodied life. What makes this period feel like an age of endless food is not that resources were infinite, but that they were reliably renewed. Seasonal cycles existed, but they were gentle. Droughts and freezes were less extreme. Entire ecosystems could recover from disturbance without collapsing. This reliability allowed food chains to stretch upward without snapping. Another crucial factor was spatial scale. Ancient ecosystems were large. Continents were arranged in ways that created broad, uninterrupted habitats. Oceans were less fragmented by temperature barriers. Migration routes were long and predictable. Animals could move with the seasons, following food rather than being trapped by geographic constraints. Large animals benefit enormously from this kind of spatial freedom. Migration allows them to track resources over vast distances, smoothing out local shortages. It also reduces pressure on any single area, preventing overgrazing or prey depletion. In a connected world, abundance becomes a shared property rather than a local accident. Competition also functioned differently. While there was competition, it was often less intense than in modern ecosystems. When food is plentiful, competition softens. Species can coexist without pushing each other to extinction. Niches overlap without collapsing. This allows size diversity to flourish, with small, medium and large animals all finding workable strategies. Importantly, abundance changes behaviour. Animals in food-rich environments do not need to take extreme risks. They can avoid unnecessary conflict. They can invest energy in growth rather than constant vigilance. Injury becomes less catastrophic because recovery is possible. Longevity increases, which further supports large body sizes. Reproduction also shifts in abundant systems. Large animals can afford to reproduce less frequently because survival rates are higher. Offspring have better chances of reaching adulthood. Parental investment pays off. Population stability replaces rapid turnover. This stability reinforces size because slow life histories become viable. As food webs expanded, they became more layered. Instead of simple chains, ecosystems developed complex networks of interactions. Large predators could specialize. Some hunted certain prey sizes, others focused on specific environments. This specialization reduced direct competition and allowed multiple large species to coexist. But abundance is not just about quantity. It is about predictability. A giant animal does not need infinite food. It needs to know, in evolutionary terms, that food will be there tomorrow, next year, and for many generations. When that expectation holds true, size becomes a rational investment. Over time, however, this abundance began to fracture. Climate shifts altered rainfall patterns. Cooling temperatures shortened growing seasons. Carbon dioxide levels declined. Plant productivity slowed. Food webs became tighter. Energy transfer became less efficient. In the oceans, changes in circulation patterns reduced nutrient upwelling in some regions. Plankton blooms became less consistent. Marine ecosystems reorganized. Large prey animals became less common or changed their behavior. This had cascading effects up the food chain. On land, expanding deserts, mountain building, and shifting coastlines fragmented habitats. Migration routes were disrupted. Seasonal shortages became more severe. Herbivores faced increased pressure. Predators faced longer hunts and lower success rates. When food becomes unpredictable, size quickly turns from an advantage into a burden. Large animals cannot simply switch diets easily. Their digestive systems are specialized. Their energy demands are high. Missing meals becomes dangerous. Recovery from lean periods takes longer. Smaller animals respond differently. They can survive on less. They can exploit new food sources. They reproduce quickly, allowing populations to rebound after shortages. In a world where abundance is no longer guaranteed, flexibility outperforms size. This transition did not erase abundance entirely, it redistributed it. Instead of supporting a few enormous bodies, energy flowed into many smaller ones. Biomass remained high, but it was divided differently. Ecosystems became more crowded, more competitive, and more dynamic. The age of endless food did not end overnight. It faded unevenly, region by region, era by era. Some pockets of abundance persisted longer than others. This is why giants disappeared at different times in different places. Where food remained plentiful and predictable, large animals held on. Even today, remnants of this ancient pattern remain. Whales thrive where plankton blooms are dense and reliable. Large herbivores persist in savannas with seasonal but predictable growth. Wherever food remains abundant and structured, size still finds a foothold. But the global conditions that once supported widespread gigantism on land no longer exist. Earth's modern ecosystems are productive, but they are also fragmented and variable. Energy is available, but it is unevenly distributed and frequently interrupted. Understanding this helps clarify why Earth no longer builds giants as it once did. It is not because life lost the capacity for growth. It is because the steady surplus that once fed enormous bodies has been replaced by a more cautious economy of energy. As we move forward, the story becomes less about how giants lived, and more about how the planet itself began tightening the flow of resources. Because once abundance fades, every other advantage of size begins to unravel, and that unraveling, slow and quiet, reshaped the living world into the one we recognize today. When we look back at the giants of the past, it can feel tempting to imagine them as the ultimate achievement of evolution, as if life was steadily building toward bigger and bigger forms before something went wrong. But evolution does not work toward peaks or final goals. It explores, it tests, it responds. And sometimes, when conditions allow, it pushes traits to extremes simply to see if they hold. Gigantism was one of those experiments. A dramatic one, yes, but also a temporary one. Evolution does not plan ahead. It has no foresight and no preference for moderation or excess. It works entirely in the present, favouring whatever traits increase survival and reproduction right now. When the environment offers stability, abundance, warmth and space, larger bodies can succeed. When those same conditions persist for long enough, size keeps increasing because nothing strongly pushes back against it. This is how extremes arise, not because evolution seeks them, but because nothing stops them. In periods when Earth favoured growth, there were few penalties for becoming larger. Predation pressure decreased as bodies grew beyond the reach of most attackers. Competition eased when resources were abundant. Longevity increased. Reproductive strategies shifted toward fewer offspring with higher survival rates. Each of these changes nudged size upward, generation by generation. But this upward drift was never guaranteed to last. It depended entirely on the continued presence of the conditions that made size workable. The moment those conditions began to weaken, the experiment entered its unstable phase. Extreme traits, by definition, sit near the edge of viability. They work well only within narrow boundaries. A giant body is highly specialized. Its skeleton, metabolism, behavior, and life history are all tuned to a specific set of environmental assumptions. When those assumptions change, even slightly, the margin for error shrinks. Evolution does not protect extremes, it abandons them the moment they stop working. One way to understand this is to think about redundancy. Smaller animals often have multiple ways to survive. They can change diets. They can shelter in different places. They can reproduce quickly and spread risk across many offspring. Large animals lack this flexibility. Their size locks them into particular strategies. They cannot hide easily. They cannot switch food sources rapidly. They cannot recover quickly from population losses. This means that gigantism is always a gamble. It pays well under the right conditions, but it carries high risk when those conditions shift. Throughout Earth's history, we see this pattern repeat. Lineages grow larger over millions of years, reaching impressive extremes. Then, as climates change or ecosystems reorganize, those extremes collapse. Sometimes the entire lineage disappears. Other times, it retreats back towards smaller forms. Dinosaurs provide a clear example. Early dinosaurs were relatively modest in size. Over time, as ecosystems stabilized and food became abundant, some lineages expanded dramatically. But even within the dinosaur era, size was not universal. Many dinosaurs remained small or medium-sized. Gigantism existed alongside other strategies, not above them. When the environmental framework that supported large dinosaurs broke down, smaller dinosaurs survived longer. Some eventually gave rise to birds. The extreme forms vanished, not because they were inferior, but because they were less adaptable. This pattern extends beyond dinosaurs. Mammals followed a similar trajectory. After the extinction of the dinosaurs, mammals diversified rapidly. Many lineages experimented with large size. Giant ground sloths, enormous rhinos, massive herbivores and predators all appeared. For a time, the experiment seemed to work again, but once more, it did not last. As climates cooled and became more variable, as ice ages reshaped landscapes, as ecosystems fragmented, those mammalian giants declined. Smaller mammals with faster reproduction and broader diets persisted. Today's megafauna are remnants, not representatives of a peak. What makes gigantism an experiment rather than a permanent trend is that it amplifies trade-offs. Every advantage gained through size comes paired with a vulnerability. Strength increases, but speed often decreases. Protection improves, but heat management becomes harder. Longevity increases, but reproductive rates slow. These trade-offs balance delicately as long as the environment remains forgiving. When conditions worsen, those trade-offs become liabilities. Evolution has no mechanism for preserving a trait simply because it was once successful. It does not remember past abundance, it only responds to present pressures. If a smaller body survives better in a new climate, smaller bodies spread. If faster reproduction outcompetes longevity, speed replaces patience. This is why extremes tend to be temporary. They exist at the edges of possibility, not the centre of stability. Another important aspect of this experiment is that it unfolded independently in different places and times. Gigantism was not a single event. It emerged repeatedly wherever conditions aligned. Marine reptiles grew huge. Terrestrial dinosaurs did the same. Mammals followed later. Even birds experimented with large forms on isolated islands. Each time, the result was similar. Large size flourished briefly, then receded. This repetition tells us something fundamental. Gigantism is not rare because it is difficult to achieve. It is rare because it is difficult to maintain. The Earth is not a stable laboratory. It is a dynamic system. Continents move. Oceans open and close. Atmospheres change composition. Climate oscillates. In such a system, traits that rely on long-term stability are always vulnerable. Evolution favours resilience over impressiveness. It favours strategies that survive disruption, not those that dominate under ideal conditions. This does not mean that evolution avoids extremes. It simply does not cling to them. Another reason gigantism remains temporary is that it reshapes ecosystems in ways that eventually limit itself. Large animals consume enormous resources. They alter landscapes. They compress food webs. Over time, this can reduce diversity and resilience within ecosystems, making them more sensitive to disruption. When a disturbance occurs, whether climatic or geological, ecosystems dominated by large, slow-reproducing animals struggle to recover. Collapse happens faster, and recovery takes longer. Smaller species then move in, filling gaps and reshaping the system around their own needs. This self-limiting nature adds another layer of instability to gigantism. The very success of giants can make ecosystems brittle. It is also worth noting that evolution does not reset experiments cleanly. When extremes collapse, the path back is not guaranteed. Environmental conditions may never align in the same way again. Oxygen levels may not rise as high. Temperatures may not stabilise for as long. Continental arrangements may prevent large-scale connectivity. This is why Earth does not simply cycle endlessly between giant and non-giant worlds. Each experiment leaves behind a changed planet. The disappearance of giants is not evidence that evolution failed. It is evidence that evolution is conservative when forced to be. It sheds excess when the budget tightens. It retreats toward forms that can survive uncertainty. And uncertainty is now one of Earth's defining features. The modern world is marked by rapid change. Even before human influence, climate oscillations accelerated. Ice ages came and went. Sea levels rose and fell. Habitats fragmented and reconnected unpredictably. These conditions strongly favour smaller, faster, more flexible life forms. Under such pressures, gigantism struggles to re-emerge. That does not mean the experiment is permanently closed. It means the door is only open under very specific circumstances. If Earth were to return to long-term warmth, high oxygen availability, stable climates, and abundant food webs, size would likely increase again. Evolution would test the limits once more. But until then, the giants remain as reminders of what happens when the rules loosen. They show us that life is not always cautious. When given the chance, it pushes boundaries. It explores scale. It builds bodies that seem impossible in hindsight. And then, when the conditions shift, it moves on without hesitation. As we continue, this idea becomes increasingly important, because the disappearance of giants was not driven by a single cause or a single moment. It was the natural end of an experiment whose success depended on a planet that no longer exists in quite the same way. And in understanding that, we begin to see modern Earth not as a diminished version of the past, but as a system operating under different constraints, favouring different solutions, and quietly shaping life toward forms that can endure whatever comes next. For a very long time, Earth appeared content with the bargain it had made. Warmth in exchange for stability, abundance in exchange for scale. Life grew large, slow, and heavy, and the planet carried that weight without complaint. But Earth has never been a static agreement. It does not promise consistency. It shifts, recalibrates, and rebalances, not abruptly at first, but quietly enough that the change is only obvious once it is already underway. When the planet began to change its mind, it did not do so with a single catastrophe or dramatic reversal. There was no moment when giants were suddenly unwelcome. Instead, the ground rules began to slide, almost imperceptibly, and life continued forward as if nothing fundamental had changed. At first, it hadn't. Not yet. One of the earliest signs was temperature. Global warmth did not vanish, but it became uneven. The gentle blanket that once covered much of the planet began to thin at the edges. Poles cooled faster than equatorial regions. Seasonal differences sharpened. Winters, where they existed, grew longer and less predictable. Summers became more variable, sometimes hotter, sometimes shorter. For small animals, this variability could be tolerated. For large ones, it introduced new costs. Large bodies are slow to respond to temperature change. They retain heat well, which is useful in cold environments, but they also struggle to cool quickly. In a world with stable warmth, this balance works. In a world with increasing extremes, it becomes dangerous. Heat waves become more taxing. Cold snaps become more lethal. Energy that once went into growth and maintenance now had to be diverted into survival. At the same time, atmospheric composition began to shift. Oxygen levels, which had once been high enough to make large bodies energetically affordable, fluctuated and gradually declined. Again, this was not sudden. There was no dramatic drop that wiped species out overnight. But even small reductions mattered. Oxygen is unforgiving that way. A slight decrease raises the cost of every movement, every heartbeat, every repair process inside the body. For animals built close to their physiological limits, that added cost narrowed the margin for error. Injuries healed more slowly. Long chases became riskier. Stress accumulated. The kinds of inefficiencies that once would have been tolerable now mattered. Food availability also began to change, though not always in obvious ways. The age of endless food did not simply end, it fractured. Productivity became patchier. Some regions remained lush while others declined. Rainfall patterns shifted. Rivers changed course. Forests retreated in some areas and expanded in others. This mosaic of abundance and scarcity favoured animals that could move quickly, adapt diets, or exploit small-scale resources. Large animals struggle in patchy worlds. Their size assumes access to large, continuous areas of food. Fragmentation breaks that assumption. Migration routes that once followed predictable patterns were disrupted. Seasonal shortages grew sharper. A missed migration window or a failed breeding season could have cascading effects. Another slow but powerful force was geological change. Continents continued to drift, altering ocean currents and atmospheric circulation. Mountain ranges rose, reshaping climate on regional scales. New barriers appeared. Old connections vanished. Oceans that had once mixed freely developed temperature gradients that separated ecosystems. This reduced the global uniformity that giants relied on. As ocean currents shifted, nutrient upwelling changed. Some regions became less productive. Marine food webs tightened. Large prey species altered migration routes or declined in number. Predators that had depended on those prey faced new challenges. Size, which once allowed dominance, now required greater effort to maintain. On land, the expansion of open environments altered the balance between predators and prey. Forests that had supported ambush strategies gave way to grasslands that favoured speed and endurance. Smaller, faster animals gained advantages. Large predators that relied on close-range power faced longer chases and higher failure rates. This shift did not immediately eliminate giants, but it placed them under increasing pressure. They could still succeed, but success required more favourable circumstances, fewer mistakes, fewer disruptions. Over time, this selective pressure trimmed the extremes. Another important change was the tempo of disturbance. Fires, storms, droughts, and floods became more frequent or more severe in certain regions. While disturbance is a natural part of ecosystems, increased frequency favours fast recovery. Smaller species bounce back quickly, large species do not. Their populations recover slowly, if at all. Each disturbance removed individuals from populations that could not easily replace them. Over generations, this mattered more than any single event. Populations thinned, genetic diversity declined, resilience weakened. It is crucial to understand that the planet did not turn hostile. It simply stopped being exceptionally generous. The baseline shifted from abundance toward variability, from stability toward fluctuation, from predictability toward uncertainty. In that new context, gigantism became an expensive habit. Evolution responded not with panic but with adjustment. Lineages that could shrink did. Those that could not disappeared. Traits that favoured flexibility spread. Reproductive rates increased. Lifespans shortened. Body plans became more modular, more adaptable. The giants that remained did so in refuges, in places where conditions changed more slowly or retained aspects of the old world, deep oceans, isolated regions, stable river systems. These pockets allowed some large animals to persist long after the global trend had turned against them. But refuges are not foundations. They delay endings, they do not reverse them. Over millions of years, the cumulative effect of these changes became clear. Earth was no longer building new giants on land. It was maintaining a few survivors, but not encouraging further growth. The experiment had run its course. What makes this transition so striking is how ordinary it was. There was no villain, no single cause, no dramatic decision. Just a planet doing what it has always done. Changing slowly enough that life has time to respond, but not always enough time to preserve its most extravagant forms. From our perspective, it can feel like a loss, a smaller world, a quieter one. But from Earth's perspective, it was a recalibration, a return to strategies that worked under uncertainty. The planet did not reject size outright. It simply stopped subsidizing it. Even today, we live in the aftermath of that shift. Modern ecosystems still carry the imprint of a world that once favoured giants. Our largest animals feel outsized because the context that produced them has mostly vanished. They are reminders of the different balance. As we move forward, it becomes clear that this change was not an ending, but a transition. The conditions that shaped life altered and life followed. Understanding this moment when the planet began to change its mind helps explain not only why giants disappeared, but why the living world now looks the way it does. And it also raises a quiet, lingering question. If Earth changed once, and life responded, what happens when it changes again? For a long time, warmth had been an unspoken ally of size. It softened the edges of survival, reduced the daily cost of living, and allowed bodies to grow large without constantly fighting their surroundings. When that warmth began to fade, the consequences were not immediate extinction, but something slower and more unforgiving. Cooling climates did not simply remove giants from the landscape. They made being huge increasingly expensive, one cost at a time. Climate cooling is rarely uniform. It does not mean everything becomes cold all at once. Instead, it introduces contrast. Hot and cold begin to alternate more sharply. Seasons grow longer or harsher. Winters linger. Summers shorten or become unpredictable. For small animals, these changes are challenging but manageable. For large ones, they are transformative. A large body interacts with temperature differently than a small one. Size slows change. Heat enters and leaves massive bodies more gradually. This can be helpful in consistently cold environments, where retaining warmth is valuable. But in climates that fluctuate, that same inertia becomes a problem. A large animal cannot quickly warm itself during sudden cold snaps, nor can it easily shed heat during unexpected warmth. It lives closer to its thermal limits, As Earth cooled overall, particularly through long-term trends punctuated by ice ages, those limits mattered more. Large animals that had evolved under relatively narrow temperature ranges now faced environments that regularly pushed them outside their comfort zones. Maintaining internal stability required more energy. Energy that once went into growth, reproduction, or recovery now had to be spent simply staying alive. For warm-blooded animals, cooling climates increase metabolic demands. Generating body heat requires fuel. The larger the body, the more heat must be produced to maintain internal temperatures, especially when moving or exposed to wind and moisture. While large bodies retain heat well, they also lose it across vast surface areas when conditions are harsh. The balance shifts from advantage to burden. Cold environments also reshape behaviour. Large animals often rely on slow, steady movement and long periods of rest. In colder climates, inactivity becomes risky. Muscles stiffen, circulation slows, energy reserves deplete. Movement becomes necessary not for hunting or migration, but for survival itself. This constant demand raises baseline energy costs. For cold-blooded animals, the situation is even more severe. Reptiles and other ectotherms depend on external heat sources to function. As global temperatures dropped and seasonal variability increased, the windows during which these animals could be active narrowed. Large ectothermic bodies take longer to warm and longer to cool. In cooler climates, that means less time feeding, digesting, or reproducing. Size, which once allowed dominance, now imposed inactivity. This is one reason why giant reptiles disappeared more completely than giant mammals. Their physiology was tightly coupled to environmental warmth. As that warmth became unreliable, their ability to function collapsed. Smaller ectotherms survived by hiding, burrowing, or exploiting brief warm periods. Large ones could not. Cooling climates also altered vegetation. Plant growth slowed. Growing seasons shortened. In many regions, lush forests gave way to grasslands, tundra, or sparse woodlands. This reduced the overall energy available to herbivores, particularly those adapted to consuming large quantities of low-quality plant material. Large herbivores depend on volume. They eat a lot, but they rely on being able to eat continuously. When plant productivity declines or becomes seasonal, that strategy fails. Missing weeks of adequate food can weaken a large body dramatically. Fat reserves help, but they are finite. Rebuilding lost mass takes time that may not be available. Smaller herbivores, by contrast, can exploit new plant types, shift diets, or survive on less. They reproduce faster, allowing populations to recover after harsh seasons. In cooling climates, flexibility beats capacity. Predators feel these changes indirectly but no less severely. When herbivore populations fluctuate or decline, predators lose reliable prey. Large predators cannot easily switch to smaller prey without increasing energy costs. Chasing many small animals is far more expensive than killing one large one. As prey becomes scarcer or more evasive, hunting success declines. Cold environments also favour speed and endurance over sheer power. Open landscapes created by cooling climates allow prey to see predators from farther away. Long chases become necessary. Smaller predators with higher stamina gain advantages. Large predators built for ambush or short bursts of power struggle to adapt. Another subtle cost of cooling climates is increased injury risk. Cold stiffens joints and muscles. Slips and falls become more dangerous, especially for heavy bodies. Injuries heal more slowly when energy is diverted to thermoregulation. A broken limb or torn muscle that might have healed in a warmer world can become fatal in a colder one. Disease dynamics also change. Cold stress weakens immune systems. Large animals with slower reproduction and longer lifespans accumulate pathogens over time. Population declines reduce genetic diversity, making disease outbreaks more devastating. Smaller animals with rapid turnover can adapt more quickly. Perhaps most importantly, cooling climates increase variability. Instead of long stretches of favourable conditions, life faces repeated challenges. One bad winter, one prolonged drought, one failed migration. For large animals, each event carries disproportionate risk. Survival becomes a gamble played with high stakes and low margins. Over time, these pressures do not need to eliminate giants outright. They simply prevent new giants from emerging. Existing large species persist until their populations dwindle, but evolutionary trends reverse. Lineages stop growing larger. Some shrink, others disappear entirely. This is why the fossil record shows a gradual decline in maximum body size across many groups as climates cooled. The ceiling lowered, the extremes retreated. The average shifted downward. Importantly, cooling did not affect all regions equally. Some areas remained warm and productive for longer, allowing giants to survive locally. This unevenness explains why large animals disappeared at different times in different places. It was not a synchronized event, but a staggered retreat. Even during ice ages, there were interglacial periods when warmth returned temporarily. Some large mammals expanded during these windows, only to contract again when cold returned. Each cycle trimmed populations further, eroding resilience. Eventually, the cost of being huge outweighed its benefits almost everywhere on land. In the oceans, the story diverged. Water buffers temperature changes. Deep currents stabilize conditions. Large marine animals can migrate vertically and horizontally to track favorable environments. Cooling climates affected them too, but less severely. This buffering effect allowed ocean giants to persist long after their terrestrial counterparts vanished. On land, gravity amplifies every cost. A large body must constantly support its own weight. In cold, resource-limited environments, that burden becomes harder to justify. Evolution responds by favouring lighter frames, quicker maturation, and lower maintenance costs. Climate cooling did not kill giants directly. It rewrote the budget. It raised the price of size until only the wealthiest environments could afford it. As those environments disappeared, so did the giants. Understanding this reframes extinction not as catastrophe, but as accounting. Energy in versus energy out. Stability versus variability. Risk versus reward. When the balance tipped, gigantism lost its economic footing. As we move forward, this cost becomes inseparable from other pressures, like habitat fragmentation and ecological complexity. Cooling climates were not acting alone. They were part of a broader shift toward a world that no longer subsidized extremes. And once size stopped being affordable, evolution did what it always does. It found cheaper ways to survive. From the outside, great size looks like strength made visible. Thick bones, heavy muscles, a presence that seems immune to threat. But size carries a quiet contradiction. The larger a body becomes, the more it depends on everything going right. What appears powerful on the surface often hides a delicate balance underneath, one where small disruptions can ripple outward with surprising force. Large animals are not fragile in the sense of being weak. They're fragile in the sense of being tightly tuned. Their bodies operate close to the edge of what their environment can support. Every system inside them is optimized for a specific range of conditions, and when those conditions drift, the consequences multiply. One of the most important hidden vulnerabilities of large size is repair. Damage happens to all living bodies. Muscles strain, bones crack, organs wear down. For small animals, injuries can be catastrophic, but recovery, if it happens, is often fast. Tissues are thin, distances are short, energy demands are lower. A small body can redirect resources quickly. Large bodies do not have that luxury. Repair takes time. Healing a fracture in a massive limb requires enormous energy investment and long periods of reduced mobility. During that time, feeding becomes harder, predation risk increases, infection becomes more likely. An injury that would be inconvenient for a smaller animal can become fatal for a larger one. Not because the damage is greater, but because recovery is slower. Movement itself becomes a calculated risk. Every step carries force proportional to mass. A misstep, a slip, a fall carries consequences that scale with size. Joints endure tremendous stress over long lifespans, where accumulates arthritis, joint degeneration, and muscle fatigue become limiting factors long before an animal reaches the end of its theoretical lifespan. This is why many large animals move carefully. What looks like slowness is often caution. Speed is possible, but it is costly. Acceleration stresses bones and tendons. Sudden turns increase injury risk. A large animal cannot afford frequent mistakes. Another hidden fragility lies in circulation. Delivering oxygen and nutrients to every part of a massive body requires complex systems operating at high efficiency. Hearts must pump powerfully but steadily. Blood vessels must withstand pressure over long distances. Any disruption, blockage, or inefficiency has far-reaching effects. As size increases, redundancy decreases. There are fewer alternative pathways, fewer workarounds. A failure in one part of the system affects the whole. Small animals can often compensate for local damage. Large animals struggle to do so. Thermal regulation introduces additional strain. Large bodies generate and retain heat. In stable climates, this is manageable. In fluctuating ones, it becomes dangerous. Overheating can occur during exertion. Cooling takes time. Heat stress damages tissue silently, accumulating over years. Cold introduces its own risks. Circulation slows. Extremities become vulnerable. Muscles stiffen. Energy drains faster than it can be replenished. Large bodies require constant thermal management, which ties survival closely to environmental conditions. Reproduction adds another layer of fragility. Large animals tend to reproduce slowly. Gestation periods are long. Offspring are few. Parental investment is high. This strategy works only when survival rates are high and environments are predictable. Any increase in juvenile mortality quickly destabilizes populations. A few bad years can undo generations of slow growth. Droughts, cold spells, disease outbreaks, or food shortages disproportionately affect large species because they cannot replace losses quickly. Smaller species absorb such shocks through rapid reproduction. Large species cannot. Disease itself becomes more dangerous with size. Long lifespans mean prolonged exposure to pathogens. Population densities are often lower, which can reduce transmission, but when disease does spread, recovery is slow. Genetic diversity may already be limited due to small population sizes, reducing resistance. Large animals also depend heavily on intact social or ecological structures. Migration routes must remain open. Breeding grounds must remain stable. Food sources must persist across seasons. Disruption of any one element can cascade through the entire life cycle. This dependence on structure makes large animals sensitive to fragmentation. When habitats break apart, when corridors close, when timing shifts, large bodies struggle to adjust. Smaller animals slip through gaps. Large ones are blocked. Even success carries risk. When large animals dominate ecosystems, they simplify food webs. They concentrate energy flow. This can make systems less resilient. When disruption occurs, there are fewer buffers. Collapse happens faster, and recovery takes longer. This is the paradox of size. The traits that make giants successful also make them brittle. Strength reduces flexibility. Efficiency reduces redundancy. Longevity reduces adaptability. None of this means that large animals were doomed from the start. In the right world, these vulnerabilities remain hidden. Stability masks fragility. Abundance cushions failure. Predictability rewards patience. But when that world changes, the hidden costs surface. The fossil record does not show giants disappearing because they suddenly became weak. it shows them declining because they became exposed. Their vulnerabilities, once theoretical, became real. Injury mattered more, disease mattered more, missed seasons mattered more. Smaller animals did not replace giants because they were superior in every way. They replaced them because they were cheaper to maintain in a more uncertain world. This fragility is not a flaw in design. It is the price of pushing boundaries. Any system operating near its limits sacrifices resilience for performance. Gigantism is performance taken seriously. Understanding this helps shift how we think about extinction. Giants were not victims of sudden failure. They were specialists whose specialization became too costly. As we continue, this fragility connects directly to how extinctions unfolded. Because once vulnerabilities are exposed, disappearance does not require catastrophe. It only requires time. And time, once the ally of giants, quietly became the force that wore them down. When people imagine extinction, they often picture drama. Fire raining from the sky, oceans boiling, landscapes torn apart in a single unforgettable moment. Those things do happen, and when they do, they leave sharp lines in the fossil record. But most extinctions do not begin that way. Most do not announce themselves. They start quietly, almost politely, as a series of small absences that are easy to ignore. Extinction is rarely loud at first because it is usually not a single event. It is a process, a gradual thinning, a slow retreat that can take thousands or even millions of years to complete. Species do not vanish overnight. They fade, often while still appearing stable on the surface. The first sign is usually not death, but fewer births. Reproduction slows, juveniles fail to survive at the same rates they once did. Breeding seasons become less successful. These changes are subtle. Populations may still look healthy for a long time, especially in long-lived species. Adults remain. Territory is still occupied. The animal still exists. But the future is already shrinking. Large animals are especially vulnerable to this quiet phase because their life histories stretch time. When an animal lives for decades and reproduces slowly, population decline can remain invisible for generations. By the time the problem becomes obvious, recovery may no longer be possible. A drought does not need to kill adults to push a large species toward extinction. It only needs to disrupt reproduction for a few cycles. A colder climate does not need to wipe out entire herds. It only needs to reduce juvenile survival slightly. Over time, those small losses accumulate. The fossil record captures this pattern repeatedly. Species appear stable, widespread, and abundant, then gradually become rarer. Their geographic range contracts. They disappear from marginal habitats first. Only later do they vanish from their core regions. By the time extinction is complete, it may feel sudden, but the process began long before. One reason extinction stays quiet is that ecosystems can mask decline. Large animals often persist at low densities. Their absence from some areas does not immediately destabilize the system. Other species fill gaps. Food webs adjust. Life goes on, just slightly rearranged. For the species itself, however, the margin is narrowing. Another reason extinction begins softly is that environmental change is often uneven. Conditions deteriorate in some regions while remaining tolerable in others. Populations retreat to refuges. These refuges create the illusion of survival. As long as a species exists somewhere, it feels as though extinction has been avoided. But refuges are fragile. They're often smaller, isolated, and more sensitive to disruption. Populations within them are vulnerable to inbreeding, disease, and chance events. A single harsh season can undo decades of persistence. Large animals rely heavily on these refuges during decline. They disappear from open plains but survive in valleys. They retreat from continents but linger on islands. They vanish from shallow seas but persist in deeper waters. Each retreat reduces options. This gradual withdrawal also affects behavior. Animals change migration patterns. They alter diets. They adjust breeding timing. These adaptations may prolong survival, but they often come at a cost. Energy budgets tighten, stress increases, lifespans shorten. At some point, adaptation itself becomes a burden. Another quiet driver of extinction is demographic imbalance. Large animals often have skewed age structures during decline. Older individuals dominate populations because younger ones fail to survive. At first, this looks stable. Adults are experienced. They hold territory. They reproduce when possible. But without sufficient young, the population is aging out. When older individuals die, there are not enough replacements. The collapse, when it comes, feels abrupt, but it is the delayed consequence of long-term failure. Disease plays a similar role. Pathogens do not need to kill large numbers quickly. They only need to reduce fitness slightly. Chronic infections weaken individuals, reduce fertility, and increase vulnerability to other stressors. In small, isolated populations, disease can circulate quietly for generations. In large animals, disease recovery is slow. Immune systems weaken under stress. Genetic diversity declines. Resistance erodes. Eventually, a disease that once caused mild symptoms becomes lethal. Environmental noise also hides extinction. Climate does not change smoothly. It fluctuates. Good years follow bad ones. Temporary recoveries occur. Populations rebound slightly, then decline again. These oscillations create false hope. From a geological perspective, extinction looks sudden, because the final disappearance is easy to mark. From an ecological perspective, it is usually the last step of a long unravelling. This is especially true for giants. Their disappearance was rarely dramatic. Megafauna did not vanish in a single moment of chaos. They became fewer. They became localised. They became vulnerable. A single storm does not doom a giant species. A pattern of slightly worse storms does. A single cold year does not end a lineage. A century of colder winters does. A single failed breeding season does not erase a population. Repeated marginal seasons do. This slow erosion is why extinction often goes unnoticed by contemporaries. Even if intelligent observers had existed alongside ancient giants, they might not have recognized the trend. The animals were still there. The world still looked familiar. Change happened below the threshold of alarm. There is also a psychological reason extinction feels sudden in hindsight. Humans tend to focus on endpoints. We remember the last sighting, the final fossil layer, the moment of absence. We rarely dwell on the long decline that led there. It is less dramatic, less satisfying. But for the species involved, that decline is the story. Extinction also tends to accelerate near the end. As populations shrink, random events matter more. A flood, a disease outbreak, a fire. What would have been survivable for a large population becomes catastrophic for a small one. This creates a tipping point where decline suddenly becomes collapse. To outside observers, this looks like sudden extinction. In reality, it is the final consequence of long-term vulnerability. The disappearance of Earth's giants followed this pattern again and again. Their populations thinned over time, their ranges shrank. Their resilience eroded. By the time dramatic events occurred, such as asteroid impacts or rapid climate shifts, many species were already weakened. This does not diminish the role of catastrophic events. It places them in context. Catastrophes often finish what gradual change begins. Understanding this quiet phase of extinction helps explain why Earth no longer builds giants. It was not a single decision or disaster. It was a cumulative narrowing of possibility. Conditions became slightly worse for large bodies, year after year, generation after generation. Eventually, the cost crossed a threshold. Reproduction failed too often. Recovery took too long. Survival required too much luck. At that point, extinction did not need to shout. It simply continued. This pattern also explains why extinction is so difficult to reverse. By the time decline is obvious, the underlying causes are deeply embedded. Habitat has changed, climate has shifted, food webs have reorganized. The world that once supported the species no longer exists. The giants did not disappear because they were unlucky. They disappeared because the environment gradually stopped paying the costs they required. Extinction was the bookkeeping entry at the end of a long accounting process. As we move forward, this understanding becomes crucial, because it reminds us that disappearance is rarely about a single mistake or moment. It is about accumulation, about margins shrinking until nothing is left to give. And once extinction reaches that quiet final stage, there is no dramatic warning. Just absence, where presence once felt permanent. Even in a world that no longer favours giants the way it once did, size has not vanished as an idea. It lingers, it tempts, it reappears in certain lineages, under certain conditions, as if evolution cannot entirely let go of the advantages that bigness once offered. Modern animals still flirt with size, not recklessly, not to the extremes of the past, but cautiously, within boundaries shaped by everything the planet has learned since. To understand why this happens, it helps to remember that the rules of size never disappeared. They were tightened. The benefits of being large still exist. They are simply harder to access and more expensive to maintain. One of the most obvious places where bigness persists is the ocean. The largest animal to have ever lived, the blue whale, is alive today. This alone tells us something crucial. Earth did not lose the capacity to support enormous bodies. It lost the ability to do so broadly, especially on land. In the ocean, many of the old conditions still apply. Buoyancy reduces the cost of mass. Temperatures are more stable. Food, when concentrated in the right places, can be extraordinarily abundant. Whales do not dominate the ocean because evolution is nostalgic. They dominate because in specific marine contexts, size still pays. A large body allows efficient long-distance travel. It allows energy storage. It reduces predation risk. It enables feeding strategies that smaller animals cannot use, such as engulfing massive volumes of prey in a single motion. But even whales show restraint compared to ancient marine giants. Their size is impressive, but it exists alongside tight specialization. They rely on specific food sources. They migrate vast distances to track productivity. They reproduce slowly. Their success is conditional. Remove any part of that system, and size becomes a liability again. On land, the flirtation with bigness is more subtle. Modern terrestrial animals rarely approach the extremes of the past, but many still push toward the upper limits of what current ecosystems can support. Elephants, rhinoceroses, giraffes, and large bovines all occupy this space. They are large enough to gain many of the advantages of size, but not so large that the costs become unmanageable. These animals benefit from reduced predation. Adult elephants, for example, face few natural threats. Size allows them to access food that smaller animals cannot, such as high branches or tough vegetation. Their large digestive systems process low-quality food efficiently. Their social structures help buffer environmental stress. At the same time, these animals reveal how constrained modern bigness is. They require extensive habitats. They depend on seasonal movements. They reproduce slowly. Their populations are vulnerable to disruption. Even without human influence, they exist close to the edge of viability. Another place where bigness persists is in isolated or simplified ecosystems. Islands, for example, have repeatedly produced large animals. Without large predators, size can increase safely. With reduced competition, energy can be allocated to growth. This is how giant birds and reptiles evolved on islands long after mainland giants disappeared. But island gigantism also highlights fragility. These large animals often vanish quickly when conditions change. Introduce new predators, alter food availability, increase variability. The same traits that allowed size to grow now accelerate extinction. Modern predators also flirt with bigness in constrained ways. Large cats, bears and crocodilians approach the upper limits of terrestrial predation. Their size grants strength, intimidation, and dominance, but they do not exceed certain thresholds. Their environments cannot support larger versions without sacrificing efficiency. Even within these groups, we see constant negotiation between size and cost. Larger individuals may dominate rivals, but they require more food. Smaller individuals may survive lean periods better. Evolution balances these pressures, producing bodies that hover near an optimal compromise rather than pushing endlessly upward. There is also a behavioural aspect to modern bigness. Many large animals rely on intelligent social cooperation or learned behaviour to offset the cost of size. Elephants use memory to locate water during droughts. Whales coordinate feeding. Wolves hunt cooperatively. These strategies reduce risk and increase efficiency, allowing size to persist where it otherwise might not. This suggests something important. Modern bigness often depends on cognition or sociality in ways ancient gigantism did not. The planet now demands more compensation for size. Raw mass is no longer enough. Physiology has also adapted. Modern large animals tend to have more efficient circulatory systems, better heat management, and more flexible diets than many ancient giants. These improvements allow size to persist in a harsher, more variable world. Even so, evolution rarely pushes modern animals toward unchecked growth. Instead, it explores size cautiously, testing boundaries without crossing them. When conditions briefly improve, animals may grow larger. When conditions worsen, selection trims size back. This dynamic is visible even within species. Body sizes fluctuate across populations depending on climate, food availability and habitat. Larger individuals thrive in productive environments. Smaller ones dominate in marginal ones. Size remains fluid, responsive rather than fixed. Another reason bigness still tempts evolution is that it remains a powerful solution to certain problems. Large size solves predation by making animals difficult to kill. It solves competition by granting access to resources others cannot reach. It solves endurance by allowing energy storage. These problems have not disappeared. They simply coexist with new ones. Evolution does not forget successful strategies. It keeps them in its toolbox, ready to use when circumstances allow. Gigantism is one such strategy. Rare, risky, but effective under the right conditions. Modern ecosystems, however, rarely offer those conditions continuously. Productivity is patchy. Climate is variable. Disturbance is frequent. Under such pressure, size becomes a gamble rather than a guarantee. This is why modern animals flirt with bigness rather than committing to it fully. They edge toward larger forms, then stop. They explore the benefits, then pull back when costs rise. It is also why bigness often appears in pulses. During warmer periods, body sizes increase. During cooler or drier periods, they shrink. This pattern has repeated throughout recent geological history. Size responds to opportunity, not ambition. Even human evolution reflects this tension. Our ancestors varied in body size depending on climate and resource availability. Larger bodies retained heat and stored energy in cold environments. Smaller bodies dissipated heat better in warm ones. Size remained adaptable. Looking forward, this flirtation with bigness is likely to continue, but within narrowing boundaries. Modern Earth does not favour extremes. It favours resilience. But resilience does not exclude size entirely. It simply demands that size come with safeguards. In this way, modern large animals are living compromises. They carry echoes of a giant-friendly past, tempered by lessons learned through millions of years of environmental change. They show us what bigness looks like when it must coexist with uncertainty. They are not failed giants. They are survivors. And perhaps that is the most important point. Size today is not about dominance. It is about persistence. The animals that grow large now do so carefully, within limits, aware in an evolutionary sense that pushing too far invites collapse. As we move forward, this balance becomes increasingly relevant, because the question is no longer why Earth stopped building giants, but why it still allows some size at all. The answer lies in compromise. In systems that can occasionally support large bodies but rarely indefinitely, in environments that reward strength but punish excess. Modern animals still flirt with bigness because the advantages have not vanished. They have simply become conditional, and in that tension between benefit and cost, we see the living world negotiating with a planet that has become less forgiving, but no less complex. If Earth were asked today to build another land giant on the scale of the past, it would hesitate, not out of inability, but out of constraint. The planet still holds vast energy, rich ecosystems, and extraordinary biological complexity, yet the way those pieces are arranged now places firm limits on how large bodies can realistically become. These limits are not artificial. They're not temporary inconveniences. They're woven into the current structure of the world itself. One of the most important limits is variability. Today's Earth is defined less by stable averages and more by swings. Temperature shifts are sharper, weather patterns fluctuate more often, seasons arrive earlier or later than expected. Even without considering human influence, the planet operates on shorter, less predictable cycles than it did during many giant-friendly eras. For large bodies, variability is costly. Size assumes continuity. A giant animal depends on the idea that next year will resemble this one closely enough for long-term strategies to work. When that assumption fails repeatedly, size becomes a liability. Modern Earth asks life to adapt quickly, not to commit heavily. Another limit lies in productivity distribution. The planet still produces enormous amounts of biomass, but it does so unevenly. Energy is concentrated in pockets rather than spread broadly across continents. Highly productive regions exist, but they are separated by areas of lower output. This patchiness fragments food webs. Large animals struggle in fragmented systems. Their energy demands are high and continuous. They cannot easily hop between distant productive zones without incurring enormous costs. Migration routes that once spanned uninterrupted landscapes now pass through barriers, bottlenecks, or unsuitable terrain. Even without fences or roads, geography itself has become more segmented. The structure of modern ecosystems also imposes constraints. Food webs today tend to be shorter and more tightly coupled. There are fewer layers of large-bodied prey supporting large-bodied predators. Energy transfer loses efficiency as ecosystems simplify. This reduces the surplus energy available at the top. In such systems, large predators face diminishing returns. Each increase in size demands more food, but the system cannot reliably deliver it. Smaller predators, which can exploit a wider range of prey sizes, gain an advantage. Evolution responds by trimming size rather than expanding it. Gravity has not changed, but its consequences have. In a world where land animals must traverse uneven terrain, cope with frequent disturbances, and recover from injuries without long periods of rest, the cost of supporting massive bodies rises sharply. Bones, joints, and muscles operate closer to failure thresholds. Wear accumulates faster than it can be repaired. Modern Earth also limits size through time pressure. Life cycles are compressed. Environmental windows open and close rapidly. Breeding seasons shift. Resource pulses appear briefly and vanish. Large animals with slow reproduction and long maturation cannot take advantage of short-term opportunities. By the time a giant body is built, the opportunity may be gone. Smaller animals thrive in this tempo. They can exploit brief abundance. They can rebound quickly after loss. They can adapt genetically within fewer generations. Size resists this pace. It assumes patience in a world that no longer offers it. Another constraint is ecological crowding. Modern ecosystems support extraordinary diversity, but that diversity comes at a cost. Many species share similar niches. Competition is intense. Space is partitioned finely. Large animals require wide margins. They need room to move, feed, and reproduce without constant interference. When ecosystems become crowded, large animals struggle to secure those margins. They either outcompete others, which destabilizes the system, or they are outmaneuvered by smaller, more flexible competitors. In both cases, equilibrium favors moderation. Disease dynamics also impose limits. Pathogens move quickly in modern ecosystems. Climate variability, habitat fragmentation, and population stress all increase susceptibility. Large animals with long lifespans and low reproductive rates accumulate risk over time. Disease does not need to be deadly to be limiting. It only needs to reduce fitness slightly. Smaller animals dilute disease effects through rapid turnover. Large animals cannot. Each loss matters more. Each outbreak leaves a deeper mark. The chemistry of the atmosphere and oceans also sets boundaries. Oxygen levels are sufficient for life, but they no longer provide the generous margins that once made extreme size easy. Carbon cycles move faster. Nutrient cycles are more tightly constrained. Primary productivity responds quickly to disruption. This tighter coupling means there is less slack in the system. When something goes wrong, effects propagate rapidly. Large bodies, which depend on slack, suffer first. Perhaps the most subtle limit is evolutionary inertia. After millions of years favouring smaller, more adaptable forms, many lineages have lost the structural foundations needed for extreme size. Body plans that once scaled upward efficiently have been reshaped toward flexibility instead. Bones are lighter, growth rates are faster, life histories prioritise speed. Reversing this trend would take immense time and stability. Evolution cannot simply decide to rebuild giants. It must walk the path back step by step, under conditions that allow each step to persist. Modern Earth rarely holds those conditions long enough. There is also a feedback effect. Large animals shape environments profoundly. In the past, those environments could absorb the impact. Today's ecosystems, already operating near capacity, may not. Introducing extreme size into such systems risks collapse rather than balance. This creates a self-reinforcing limit. Because large animals are harder to sustain, ecosystems evolve without them. Because ecosystems evolve without them, the conditions that would support them disappear further. The oceans remain an exception, but even there, limits are tightening. Large marine animals rely on highly specific productivity patterns. When those patterns shift, populations decline quickly. The ocean still allows size, but only within narrowing corridors. On land, the ceiling is lower, not fixed, but constrained by multiple overlapping pressures. Any one limit might be manageable. Together they form a barrier that is difficult to cross. This does not mean Earth is weaker or diminished. It means it is operating differently. The planet now favours resilience over extravagance. It rewards systems that can bend without breaking. Size can exist, but only if it comes with safeguards. Modern large animals reflect this compromise. They are impressive but cautious. They rely on behaviour, intelligence and social structures to survive. They do not rely on mass alone. If Earth were to change again, slowly and gently some of these limits might ease. Warmer, more stable climates, broader productivity, longer periods without major disruption. Under those conditions, size might begin to creep upward once more. But as things stand, today's Earth sets a clear message. Grow, but not too much. Persist, but stay flexible. Take advantage of abundance when it appears, but do not build a body that assumes it will last forever. These are not arbitrary rules. They are the result of millions of years of adjustment, written into the structure of the planet and the life it supports. Understanding these limits does not make the world feel smaller. It makes it clearer. It shows us that gigantism was not magic, and its absence is not loss. It was a response to a specific balance that no longer exists. And as we move toward the final parts of this journey, that clarity helps answer a lingering question. If Earth no longer builds giants, is that the end of the story, or simply another pause in a much longer conversation between life and the planet it inhabits? When we look around the modern world, it is easy to conclude that giants belong firmly to the past. Fossils in museums, illustrations in books, names spoken with a sense of finality. And yet, the story is not quite that closed. The disappearance of giants feels permanent only because we measure time in human scales. Earth operates on a different clock entirely, one where absence does not always mean conclusion. So the question becomes less dramatic, but more interesting. Are giants truly gone, or are they simply waiting for the right conditions to return? To approach that question honestly, it helps to strip away the idea that gigantism is a one-time achievement. It is not a ladder climbed once and then abandoned. It is a pattern that has emerged repeatedly whenever the planet allowed it. Giants have appeared, disappeared, and reappeared in different forms across hundreds of millions of years. Their absence now may be less like an ending and more like an intermission. The key word here is conditions. Giants are not built by intention, they are built by alignment. When warmth, oxygen availability, food abundance, and long-term stability line up for long enough, size becomes viable again. Evolution does not need to invent anything new. It simply extends what already works. This is why the ocean matters so much to this question. The ocean still supports giants because it still retains many of the conditions that once existed more broadly on Earth. Temperature changes are buffered. Food can become locally abundant in enormous quantities. Movement is assisted by buoyancy. Space is vast and continuous. Whales are not relics clinging to extinction. They are proof of concept. They demonstrate that the planet has not lost the physical ability to sustain massive bodies. What has changed is where and how often those conditions occur. On land, the picture is more constrained but not completely closed. Large animals still exist. They just stop at a certain size. This suggests not an absolute barrier, but a ceiling imposed by current circumstances. Ceilings can rise or fall. Throughout Earth's history, that ceiling has moved repeatedly. During warmer periods, body sizes tend to increase. During cooler or more variable periods, they decrease. This pattern appears in mammals, reptiles, and even insects. Size tracks opportunity. If the planet were to enter a prolonged period of warmth and stability again, with high productivity and reduced seasonal extremes, there is little reason to believe size would not increase once more. It might not recreate the exact forms of the past, but the underlying trend would likely reassert itself. However, waiting does not mean inevitability. Modern Earth carries complications that did not exist before. Ecosystems are more interconnected, but also more fragile. Nutrient cycles move faster. Disturbances propagate more quickly. Even under favourable climates, maintaining long-term stability may be harder now than it was in deep time. Another factor is evolutionary momentum. Many modern lineages have spent millions of years adapting to smaller body sizes. Their skeletal structures, growth rates, and life histories reflect that. Growing large again would require not just opportunity, but sustained opportunity across many generations. Evolution can do this, but it is slow. Giants are not built quickly. They require patience on geological scales. Any interruption resets the process. There is also the question of competition. Modern ecosystems are crowded in different ways than ancient ones. Many niches are tightly filled. Growing larger is not always advantageous when competitors are fast, adaptable, and numerous. Size may reduce predation risk, but it increases competition for resources. This makes future gigantism more likely in simplified systems, places with fewer competitors, regions with abundant, predictable resources. environments where complexity is low enough that large bodies can dominate without constant challenge. Historically, this is why giants often appeared in oceans, floodplains, or isolated landmasses. Those conditions still exist, but they are less widespread. Another possibility is that future giants may not look like the ones we remember. Past giants often followed familiar body plans scaled up. Future giants, if they emerge, may rely more heavily on behaviour, cooperation, or physiology to offset costs. They may be large, but not massive in the same way. Tall rather than heavy. Long rather than bulky. It is also possible that future giants will exist only briefly. A pulse rather than an era. A few million years of favourable conditions followed by retreat. In Earth's timeline, that is still meaningful, even if it feels fleeting to us. The question of waiting also invites us to consider what we mean by gone. Giants are absent from most landscapes, but their influence remains. Ecosystems still bear the imprint of a world once shaped by large bodies. Soils, plant distributions, and animal behaviours reflect interactions that no longer occur. In some sense, giants are already present as ghosts in the system. Their absence shapes what exists now. This absence itself is a condition. It opens niches. It changes flows of energy. It alters the rules under which future life evolves. Waiting, then, may not be passive. It may be preparatory. The world is adjusting to a giantless state, learning new balances. If giants return, they will do so into a very different context. There is also the uncomfortable reality that humans now represent a force comparable to geological change. Our activities reshape climate, landscapes, and ecosystems on timescales far shorter than those that once governed evolution. This introduces a new kind of uncertainty. From one perspective, this makes the return of giants less likely. Rapid change disfavours large, slow-reproducing species. From another perspective, it creates novel environments and resource distributions that could, under specific circumstances, favour size in unexpected ways. This is not a prediction. It is an observation. Life responds to conditions, not intentions. If the future offers long-term stability, size may return. If it offers volatility, size will remain constrained. The deeper point is that gigantism is not a memory. It is a capacity. Earth has demonstrated it many times. The disappearance of giants reflects a shift in priorities, not a loss of ability. When we ask whether giants are gone or waiting, we are really asking whether Earth will again provide the patience and generosity required to build them. That question does not have a fixed answer. It depends on trajectories still unfolding. From a human perspective, giants feel like something we missed. From Earth's perspective, they are one of many possible outcomes, not the default state. If they return, they will not do so suddenly. They will begin quietly, as they always have. Slight increases in body size, gradual extension of lifespans, slow shifts in energy budgets. No announcement, no spectacle, just the math beginning to work again. Until then, the absence of giants tells us something important about the present. It tells us that the world we live in rewards caution, efficiency, and flexibility. It tells us that extremes are expensive. It tells us that the planet is currently negotiating with life in a different tone. Giants are not gone in the sense of being forbidden. They're absent in the sense of being unaffordable. And affordability is not permanent. As Earth continues to change, slowly or quickly, that calculation may shift again. Whether it does in ways that invite giants back is an open question, written not in prophecy, but in climate patterns, energy flows, and time. For now, giants remain a reminder, not of failure but of possibility, a demonstration of what life can do when conditions allow it to stretch without snapping. And that possibility, quiet and patient, is never entirely erased. As this long journey begins to slow, the world we return to may feel quieter than the one we started in. The oceans no longer carry shadows the size of ships just beneath the surface. Forests no longer bend under the passing of animals taller than houses. The ground beneath our feet feels lighter somehow, less burdened by mass, less shaped by bodies that moved slowly but irrevocably through their environments. It is easy to mistake that quiet for absence, to assume that something essential has been lost along the way. But the truth is more subtle. The Earth we live on now is not a diminished version of its past. It is a different version. A planet that has traded scale for intricacy, enormity for resilience, excess for balance. Where there were once fewer bodies of overwhelming size, there are now countless forms of life negotiating space in far more complex ways. The spectacle has changed, but the creativity has not. A smaller world does not mean a simpler one. Today's Earth is dense with interaction. Every patch of soil hosts networks of roots, fungi, bacteria and insects engaged in constant exchange. Every forest canopy holds layers of life stacked vertically, each one tuned to slightly different light, moisture and temperature. Every ocean current carries not just water, but nutrients, signals and living things riding invisible highways across the planet. The disappearance of giants did not empty the world, it redistributed its attention. Where energy once flowed into a few massive bodies, it now flows through many smaller ones. Where dominance once shaped ecosystems from the top down, influence now emerges from countless interactions at every level. The drama is quieter, but it is everywhere. This shift asks something of us as observers. Giants were easy to notice. They announced themselves through size alone. You did not need patience to be impressed by them. You needed only to look up, or look out, or imagine standing beside them. Modern wonder often requires something different. It asks for attention rather than awe. Consider the animals that now carry echoes of the giant-friendly past. Whales moving slowly through cold water, their bodies tracing paths shaped by ancient abundance. Elephants walking long distances guided by memory older than any map. Trees growing for centuries, reaching heights that rival buildings, quietly recording climate in their rings. These are not remnants clinging to extinction. They are adaptations that still work, carefully calibrated to a world that no longer forgives excess easily. Even smaller creatures reflect this adjustment. Birds that migrate thousands of kilometers with bodies light enough to survive unpredictability. Predators that rely on cooperation rather than sheer mass. Insects whose brief lives and rapid reproduction allow them to track change almost in real time. These are solutions suited to the present tone of the planet. There is a temptation to romanticize the past, to imagine that a world with giants must have been richer, more alive, more complete. But abundance is not measured by size alone. It is measured by how many strategies can coexist without collapse, by how much change a system can absorb and still function. By that measure, today's Earth is extraordinarily alive. The absence of giants also tells a deeper story about time. Giants required patience. They took millions of years to build and millions more to maintain. Their disappearance reminds us that nothing in nature is guaranteed permanence, not even success, especially not success built on narrow margins. This lesson applies far beyond paleontology. It speaks to how systems behave when they grow too specialized, too dependent on stable conditions. It reminds us that adaptability often outlasts dominance, and that flexibility can be more enduring than power. The giants were not wrong for existing. They were right for their time. And that time passed. In their place, Earth now favors strategies that can bend, that can recover, that can fragment and recombine. Life has become more modular, more responsive, more distributed. The planet has not grown cautious. It has grown practiced. There is something quietly reassuring in that. A world that no longer builds giants is not a world running out of ideas. It is a world that has learned how costly some ideas can be. It is a world that prefers solutions which survive surprise. That preference shapes everything we see around us. It shapes the rhythm of seasons, the movement of animals, the way ecosystems respond to disturbance. It shapes the fact that no single species now dominates the planet through size alone. And in that balance, there is room for wonder of a different kind. Wonder in noticing how finely tuned modern life is, how much coordination is required to keep even small systems functioning, how many dependencies exist beneath what appears simple. A meadow is no longer just grass and flowers. It is a living conversation between soil chemistry, microbes, insects, weather, and time. A coral reef is no longer just colour and movement. It is a structure built by countless tiny organisms, vulnerable yet persistent, complex beyond any single creature's control. Even absence becomes meaningful. The empty niches where giants once lived are not voids. They are spaces that have been reallocated, reshaped, filled differently. The planet remembers where giants stood, not in nostalgia, but in structure. This perspective also invites humility. Humans, for all our technology and reach, are not exempt from the same rules that governed giants. We too rely on stability, abundance, and predictable systems. We too operate near the edge of what the planet can support. The story of giants is not just about the past. It is a mirror held up to the present. It shows what happens when size and complexity outpace resilience. It shows how slowly decline can begin, and how final it can become once thresholds are crossed. But it also shows something hopeful. Life does not give up when conditions change. It reorganizes. It experiments again. It finds new ways to persist. The wonder of a smaller world lies in that persistence, in the fact that even without giants, Earth continues to produce beauty, complexity, and surprise, in the fact that life does not require spectacle to be meaningful, in the fact that a planet capable of building giants is also capable of thriving without them. As this reflection settles, it may help to notice the present moment, the weight of your body supported by the ground, the air moving gently in and out, the quiet complexity that keeps everything functioning without announcement. This is the world as it is now, not grand in scale, perhaps, but deep in detail. If any part of this slow exploration brought calm, curiosity, or a sense of quiet perspective, a simple like or subscription helps keep this space open for others who might appreciate the same gentle pace. These small signals allow slow ideas to continue finding their way through a very fast world. There is no need to rush away from this thought. The story of giants does not end with their disappearance. It continues in every living system that learned from their rise and fall. It continues in a planet that adapts, recalibrates, and carries on. A smaller world, yes, but still full of wonder. And that wonder is not behind us. It is all around us, moving softly, waiting only to be noticed.